So this is a continuation of the steam system discussions that were covered in the olefins plant steam system lesson. Specifically, what we're going to talk about is a two-valve extraction turbine control, where the priorities are power and the turbine inlet steam pressure, or turbine inlet steam flow, technically. Generally, what the customer is trying to control is the pressure in the inlet header to the front end of the steam turbine and the speed of the turbine for managing the compressor or some aspect of the process. So the pressure and speed are actually controlled by PID controllers. So there'd be a pressure controller and a speed controller, the outputs of which would go to our two-valve algorithm. It controls flow and power. The two valves that we're going to manage are V1 and V2. V1 is used to control the steam to the high pressure section, and V2 is used to control the flow into the low pressure section. If those flows aren't equal, you have extraction, or at least you will have extraction if the high pressure flow is greater than the low pressure flow. A non-return valve is in the extraction line of the high pressure, or coming off the exhaust of the high pressure stage to block reverse flow through the machine. So we're talking again about a power inlet pressure priority setup for the two-valve algorithm, but as I said, technically it's not pressure, it's flow that we're managing. So let's take this turbine model and look at it a little more closely. We're going to label the inlet pressure or header, or the inlet flow, steam header to the turbine, the SHP header for super high pressure, and HP for the extraction header. So we're going to manage speed, so we need to measure the speed, usually with mag pickups, and that's the highest or first priority. The inlet steam header pressure is the secondary priority. So as long as there's no limits, we'll control both of those parameters. If we run into any kind of limits, then we sacrifice the inlet header pressure and only control the speed. We'll draw a box here to represent the two-valve algorithm to show how all of this interacts. So we bring in the speed, not the speed, we bring in the output of the speed controller and the output of the inlet header pressure controller to the two-valve algorithms as demands. Those are demand 1 for the power and demand 2 for the flow. There's outputs from the two-valve algorithm that manage each of those valves, but the two-valve algorithm doesn't directly connect the pressure controller necessarily to the to V1 or the speed controller to V2. It has to decide which valve to move based on different changes that happen to the system. So the demand 1 is a power demand, demand 2 is a flow demand, specifically in this case the inlet steam flow demand. So what are the dynamics of the steam header pressure, or the management of that pressure? The steam header can be represented as just a volume. So we're going to look at how the flow in and out of that volume is going to affect the pressure. So a pipe, which is really all the steam header becomes a volume by looking at the length and the cross-sectional area. So we'd have a total length of pipe from the steam generator to the inlet of the turbine with some diameter. So that allows us to calculate the volume. Pretty straightforward. I think you probably learned that in 6th or 7th grade. So, given the volume, how does that relate to pressure? So the pressure in the pipe is a function of the time integral of the flows in and out of that pipe. So if there's no change in the flow into or out of the pipe, in other words, the flow coming in is equal to the flow going out, there won't be a change in pressure, given that everything else is held constant, like temperature and volume. So the volume shouldn't change, and we're going to assume that the temperature is constant. So the dynamic that we're looking at for the flow is effectively the time derivative of the flow, which is influenced by the flows in minus the flows out. So if you've got more flow coming in than going out, the pressure is going to go up. If it's more going out than in, then the pressure will go down. Or if they're equal, the pressure should be equal or should be constant. So the flow in is effectively, in this model, the flow from the steam generator, and the flow out will be the steam that's taken in through V1 and into the turbine. Now, additionally, you could have flow coming out because of a pressure reducing valve that opens on an overpressure situation. That's only going to happen if the turbine can't handle all the flow that the steam generator is producing. So, looking at Avogadro's law, the old PV equals nRT, well, you can expand that to the weight flow instead of the mole flow, and temperature and gas constants. So to isolate the pressure, we divide it by both sides by V, and that way, if we want to look at a time derivative of the pressure, which is the change in pressure we're trying to manage, that's going to be the change in the weight flow times temperature over volume. So if the pressure, well, given constant temperature, the pressure, it will vary with directly with changes in the net flow through the pipe, and inversely with the volume. So if you have a very large header, a large volume, that's going to mean that for a given flow change, you won't have as big a change in the pressure. Likewise, a smaller header is going to make the pressure move more significantly with the same change in flow. So if the net flow is zero, in other words, the flow in, all the flows in are equal to the flows coming out of the header, then you'll have no change in the pressure. So constant flow gives you constant pressure. I mean, constant, or no net change in the flow. So to summarize that, if you want to hold the turbine inlet header pressure constant, you've got to react to the changes in the inlet flow by making an equal change at V1 of the steam turbine. So the pressure controller has to change the flow through V1 in response to pressure changes in the header. So let's kind of look at what a pressure controller is going to look like. Now we're just going to look at how the pressure controller would manage a valve directly to keep a pressure constant in a pipe header. So you've got a set point that you're trying to manage or keep. So let's say we're trying to keep the header pressure at 100 bar. You have to take a measurement of that pressure so you can react to it. So let's draw the header. It's going to have a valve coming off of it that will pass flow to some lower pressure. If we have flow into and out of that header, then we can watch the pressure through a transmitter. So we'll draw a line around to our measurement on the pressure controller, and what we've got now is a closed loop control system. The pressure controller will open or close V1 to balance the flows in and out of that header to keep the pressure constant. So if W1 is equal to W2, V1 doesn't need to do anything. So if the pressure measurement then is a little bit higher than the set point, or at all higher than the set point, and you want to get back to the set point, you've got to change the flow through V1. You've got to increase the flow through V1 to get the pressure back down to the measurement. In other words, the flow through V1 must be increased to cause the pressure in the header to drop if you're above set point. So we need that time differential of the pressure to be negative if we want the flow to come, if we want the pressure to come down, right? If pressure's high, we need to have a negative change in the pressure over time to get where we want to be. And from our earlier relationship, we saw that the time derivative of the flow has got to be negative there. They move together. Since the flow through V1 is a negative flow relative to the header, in other words, by our definition, flow that comes into the header is positive, flow that goes out is negative. We want to make dW/d2 a negative value if we want to get the pressure to drop, and that means we've got to increase the flow through V1 in order to create a negative time differential of the flow. So the demand to the two-valve algorithm block is, in other words, demand 2, that demand has to increase if we want to drop that pressure. So now let's take this pressure controller example and integrate it into the two-valve algorithm. So when we have the two-valve algorithm in play, it controls the valve positions on the steam turbine. We don't directly send the output of any controllers to the V1 or V2 on the turbine. So let's move that pressure controller up so that it now becomes a demand to the two-valve algorithm. Kind of redrawing some of our lines here. That pressure controller, its output is going to go in now to demand 2 on the two-valve algorithm. And instead of it controlling V1, we're going to have an output from the two-valve block that manages V1. Now, as it happens, the only valve on a two-valve steam turbine that can control the inlet header pressure is V1. Any changes to V2 are not going to affect V1, and that's because we've got sonic velocities in the valves and nozzles inside the turbine. So being critical flow, the downstream pressure changes that caused by V2 are not going to change the inlet header flow unless we blocked it in completely. But if we do change the position of V1 to manage the flow out of the inlet header, that flow is going to affect the HP section flow, which will in return or in effect or the result of that will be that it'll change the power produced by the high pressure section. So if we want to increase the flow through V1 to cause the pressure to get back in balance on the inlet header pressure, we're going to produce more power than we were before. But if our load doesn't need more power, that would cause a speed error. Now the speed of the turbine is a function of the net power that we produce, and net power I'm referring to here is the turbine power minus the compressor power. So if the net power is 0, the turbine speed is going to be stable. If the turbine power is greater than the compressor power, you'll accelerate. If it's less than the compressor power, you'll slow down. So, if we want to look at some algebra and calculus like we did on the flow example, the time rate of change of the speed, which would be acceleration, is a function of the time derivative of the power and inversely proportional to the inertia. So in other words, if we have a high inertia in our rotor, that'll resist any changes in the speed for a given power imbalance. So if you have a heavier rotor, it takes a bigger imbalance to get the same acceleration. Now that's not to say that you won't accelerate, it's just the rate of acceleration will be slower. But that's one of the things that we're trying to influence here is the acceleration of the turbine as well with our speed controller. So going back to our model here of the control system, we've got to make room for a turbine now. So we have V1 drawn on here to manage the inlet header pressure. It's going to come into the front end or the high pressure section of the turbine, and then we need a low pressure section to make up the power that we can't get from the high pressure section. The total power produced by the turbine is the power produced by the high pressure section plus the power produced by the low pressure section. So we'll draw in a valve for the low pressure section, which is our V2 valve, and get it all connected in the system. So it gets the V2 valve gets its steam from the exhaust of the high pressure section. Of course, additionally, the exhaust is plumbed to the extraction header. We're not going to show that here. You've seen it before. So any steam that comes in V1, if we can't pass all of that steam through V2, then we'll have a net flow going out through the extraction header. Okay, so for controlling speed, we have to measure speed. Then we pass that speed measurement into the speed controller, and the output of the speed controller is going into our two-valve algorithm as a speed demand. The speed demand is going to can actually influence or is influenced by both V1 and V2. So in this case where we said we had a change in flow through V1 because we had an imbalance in the inlet header pressure, we've got to make a move on V1 to get more steam through the machine, but that would upset the horsepower balance that we had and change the speed. So our two-valve algorithm is clever enough to know that any change that we make in V1 is going to change the horsepower contribution of the high pressure section, and so the V2 has to make up for that by pinching off to keep the power in balance. So if the V1 flow increases, we're going to see an increase in the power through the high pressure section of the turbine. The increase in power will increase the speed of the turbine if we don't do anything else. If we don't make some reciprocal change with V2. So the two-valve algorithm has a model of the turbine flow and power characteristics built in, and so it can calculate the change in power caused by that additional flow that we are bringing into V1. The algorithm then simultaneously calculates how much it needs to move V2 to get that or to keep the power in balance. So it knows if I move the valve V1 by, say, 2%, it can calculate exactly how much change V2 needs to move based on the power contribution of the back end of the turbine to keep a net power of 0. And so you can have changes all day long in the V1 position and never see a change in V2 if you've got all the modeling parameters balanced out. So when the inlet header flow demand changes, the two-valve algorithm makes changes to both V1 and V2 at the same time to provide the required flow change without changing the net power. So that's the two-valve algorithm. Pretty cool stuff.